Alright, Jessica, this is number 14. I'll be kind of going back and forth between the computer and here just so that I can answer your questions. So for number 14, you're going to put those values, let me pull it up, you're going to put those values in L1 and L2. So L1, L2, the X values always go in L1 and the Y values always go in L2. So using the values you sent me, 1, 5, 8, 8, and 9, then L2, 1.2, 1.8, 1.9, 2, and 2.4. And then if you want to see your scatter plot, you go to second, y equals, turn plot 1 on. You would choose the first plot, which should be L1, L2, and then zoom 9, and you can see your scatter plot and find the one that matches. And then for the R value, you have to turn your diagnostics on. So second, 0, you just keep going down. You can just hold the down key until you get down to the D's. Diagnostic on, hit enter and then enter again, and then you'll go to stat, over to calculate. You can use option 4 or option 8. I think in the video I used option 8, it doesn't matter. They're both linear regressions. And then there's your R value right there. If it doesn't show up, that means your diagnostics are not on. So 0.941. And then the relationship, if this is a positive number, it's a positive relationship. If it's a negative number, it's a negative relationship. The closer it is to 1, the stronger the relationship. So this one's pretty close to 1. So a positive linear relationship exists. And that's it for that question. All right, your next question was number 15. I think it's the same chapter, chapter 4. And this question's kind of long. It won't be this long on the final, but it's kind of a long question for the practice final. So again, if you go to stat edit, you can clear out L1 and L2 by going up and then pushing clear. And we'll put the new numbers in, 0, 1, 2, 3, and 4. And then 88.4, 85.5, 81.6, 74.7, and 76.8. And then it wants the equation, so stat calc. You can use option 4, which has the slope first and then the intercept, or option 8, which has the intercept first and then the slope. In the problem though, it wants the slope first, AX. So you can choose option 4, and then it gives you A and B. So the way this works, y hat equals, it says AX plus B. A is negative 3.4, and B is 88.2. And it would be positive. So there's your slope and your intercept, and it doesn't need to round, so we'll just type in negative 3.4 for the first blank, 88.2 for the second blank. It says to interpret the slope. The slope tells you an increase or decrease per unit. So it's an increase or decrease in y per each x unit. And that I did go over that in the chapter 4 videos. So for this one, the slope indicates the average change and final exam score for each additional absence. So it's how much is the exam score changing as the number of absences change. And then for the intercept, the y-intercept is when you do not have an x value. So an x value is 0. In this example, the x value is the number of absences. So when you have no absences, this is your predicted score. So the y-intercept indicates the final exam score if a student has no absences, for a student with no absences. And then predict the final exam score for a student who misses 4 class periods. So this is part C. Predict the final exam score for a student who misses 4, so an x equals 4 absences, and compute what's called the residual. Now the residual would not be on the final, but I do want to show you how it's calculated. So x equals 4, we're going to take this equation, y hat equals negative 3.4x plus 88.2. We're going to plug in 4 for x. You can just let the calculator do this. Negative 3.4 times 4 plus 88.2. And that gives you 74.6. That is what we call a predicted value. It's not the actual value, it's just a prediction. So we use the calculator to get 74.6. And then the residual is the difference between the prediction and the actual grade. So for the second part of that, this is predicted. We look at the chart. The chart will determine our actual. So for 4 absences, it shows 76.8. And the residual is the actual minus the predicted. And that is on your chart in chapter 4. Residual is observed minus predicted. So we're going to take what was observed, 76.8, and subtract the prediction. Now what was observed was higher than what was predicted. So we have what we call a positive residual, positive 2.2, which means the actual grade is higher than the predicted grade. So the residual is 2.2, and the final exam score is above average because it is above the regression line. It would be above what they were predicting. So we're just going to show this on a graph. So we have, again, if you want to look at your plot, you go to Zoom 9. It looks like the grades are going down, so your line of best fit is there. The residual is a vertical distance between actual and predicted. So you're going to choose the R value that goes from the pink line up to the data point. And the residual part will not be on the final. It's just a way to compare the prediction to the actual. As long as you know how to get the LSRL and know how to get the R value, that's what's going to be on the final. All right, your next question. Let's see. Your next question was number 20. Number 20. Let's see what that one looks like. This one comes from Chapter 6. Chapter 6 is the most challenging chapter for most students, so just make sure you fully understand what you're looking at here. This one question covers pretty much everything from Chapter 6 that you'll need to know. So it says, according to an airline, flights on a certain route are on time 90% of the time. So the probability is 0.9 or 0.90 for on-time flights. Suppose 17 flights are randomly selected, so our sample size is 17, and the number of on-time flights is recorded. Use technology to find the probabilities. Use the Tech Help button for further assistance. Now, Tech Help has a lot of different technology. We're going to be using the graphing calculator. So for part A, it says determine whether this is a binomial experiment. Remember, there are 4 conditions for a binomial experiment. If it meets all 4 of those conditions, it is a binomial experiment, which in this example it is. All right, part B. Part B asks for the probability that exactly 15 flights are on time. The keyword there is exactly, and that means we're using equals. That is the function binomial PDF in the calculator. The first thing you put in is the sample size, and then the probability of success, and then the target value, which is 15. PDF will do exactly 15. So that function can be found under second vars in the calculator. Vars stands for variables, so second vars. And you're going to go down to binomial PDF. You'll put in the three things, 17, comma, 0.90, comma, 15. And that will give you your exact answer, 0.2800. So I'll put that in. The next question, it asks you to interpret this. This is 28%, so it would be in 100 trials we would expect 28 to have exactly 15 on time. And then the second question, the third part C, the probability that at least 15, now this is trickier, at least 15 flights are on time as X is greater than or equal to 15. This is the hardest part. This is from section 6.2. For some reason, this is the most challenging part of the course for most of my students. The way I taught it is to make a list from 0 to the sample size of 17. 6, 7, 8, you can keep kind of skip a few. 13, 14, 15, 16, 17. You don't have to make the whole list as long as you have the idea of the number 0 through the sample size. So you stop at the sample size. Then you have to think about the phrase at least 15. That would be 15, 16, or 17. So our cutoff point would be between 14 and 15. I talked about that the calculator can only go from 0 to what we call the stopping point. And the stopping point is always the number right above the line. So for greater than, we're always going to do 1 minus binomial CDF, C for cumulative, because we want more than one value. We want 15, 16, and 17 all together. We still do sample size, probability of success, and then you put the number right above your line as your last value. So in this example, it would be 14. And you can do that in the calculator. 1 minus, then call it binomial. This time we're going to use CDF. So 1 minus, and then call up binomial CDF. 17.90 and 14. And our answer is 0.7618. Type that in. And to me, that's the hardest type of question, those greater than questions. And a student came up with this technique, and it seems to work pretty consistently. If you make your list from 0 to your sample size, draw your cutoff line, and remember that your calculator is going to stop right above that cutoff line. And if you need the greater than part, you have to do 1 minus. So I found that technique to be the most consistent. Otherwise, this can be really confusing. So again, we just interpret what this number is. It's about 76 out of 100. Part D. Part D says the probability that fewer than 15, so that'd be strictly less than 15. That would be anything from 0 to 14, so using the same list, it's any value between 0 and 14. And since we want from 0 to 14, that's the less than side, we don't need to do 1 minus, we can just do binomial CDF, 17.90 up to 14. So we want fewer than 15, which is anywhere from 0 to 14. So we call up second vars again, down to binomial CDF. This time we don't put the 1 minus first, just binomial CDF, 17.90 up to 14. 0.2382. It should be the opposite of this one. Not that you need to know that relationship, but these do all kind of go together. So this answer would be 0.2382. Let me get there. 0.2382. And again, interpreting that, that's about 24%. And the last question is going to be the trickiest. There's two different ways to get this answer. It just depends on your preferences. So part E says the probability that between 13 and 15, it says inclusive, which means including 13 and 15, are on time. So between 13 and 15, using the same chart on the side, we're looking at 13, 14, and 15. There's two ways to do this. You can do a binomial PDF of 13 and a binomial PDF of 14 and 15, like we did in part B, and do a PDF of each one and then add them all together. The shorter way is to do a binomial CDF of everything up to 15, so up to your top number, and subtract binomial CDF of everything up to just before your interval, so that would be 12. So you go one less than your bottom number, which would be 12. So some students can see that. You go all the way up to your highest number and then subtract all the way up to right before your bottom number, one less than your bottom number, so one less than 13 is 12. Some students cannot see that, and so they just do a PDF of 13, a PDF of 14, and a PDF of 15, just like we did in part B. They do just like that for all three, and then add all three answers together. You will get the exact same thing no matter which way you do it. So I like the subtraction way. I'm going to do a binomial CDF. Make sure you can see that. Binomial CDF, 17.9 and 15 minus, and then I'll call it again, second bars, binomial CDF, 17.9 and 12. So you can do that all together, and it just spits out the right answer, 0.4961. And then again, that's about 50%. Alright, so that's a really long question. That's probably going to be the most challenging. On the final, it will not have so many parts, but I just wanted you to be able to practice each type of question I might ask you. An exact, a greater than, a less than, and a between. So it has an example of each type of question I could ask from Chapter 6. Alright, that was a long question. Looks like you have another one from Chapter 6, question number 21. Alright, question number 21. According to the Almanac, 60% of adult smokers started smoking before turning 18 years old. So our probability here is 0.6. Compute the mean and the standard deviation of a random variable x, the number of smokers who started smoking before 18 in 300 trials of the probability experiment. So that's part A. We're going to go to our chart in Chapter 6, if that's binomial. And in Chapter 6, we're over here. So there's the equations if you're using the chart. This does not have a chart, so we're over here in binomial. The mean is n times p, and the standard deviation is that formula. So let me write that down. The mean is n times p. The standard deviation is the square root of n times p times 1 minus p. So we're going to use those two formulas to help us. N is 300. times P is 0.6, and 300 times 0.6 is 180. And then the standard deviation is the square root of 300 times 0.6 times 1 minus 0.6, which is, you can do all that at the same time, 300 times 0.6. And I know that 1 minus 0.6 is 0.4, so I'm just going to put in 0.4. And we square root the whole thing. You should get 8.4853. So we'll type those in. The mean is 180. Standard deviation says round to the nearest tenth, so that would be 8.5. Part B, what is the correct interpretation of the mean? So this is what we call the expected value. It would be expected out of a sample of 300, 180 of them to start smoking before they are 18. And then part C, would it be unusual to observe 240 smokers who started smoking before turning 18 in a random sample of 300 adult smokers? So our X value here is 240 out of 300. So what I would do, I wouldn't use the out of 300. A couple different ways to do this. I think the easiest thing to do is to take the expected mean with a rounded standard deviation and draw yourself a bell curve. Nice and big so you can see it. The mean in the middle, 180. And then we'll add the standard deviation 3 times. 1, 2, 3. Just to be even, I also like to subtract 3 times, just so I can see the full picture. Whoops. It's 197. And one more time. 205.5. Now we're looking at 240. Now I'm going to go ahead and fill in the other side just for consistency. Alright, but we're looking at 240 now. Hopefully we understand the bell curve enough that we understand that 240 is way, way, way out there. Very, very, very extreme. And without even needing a z-score, we can tell that 240 is going to be very unusual. You can technically get a z-score and be a little bit more precise, but if you can draw the curve and you see your mean and use your standard deviation, you can just see that 240 is going to be so far in that tail, it will be very unusual. So we can say that yes, 240 is more than 2 standard deviations away, so it would definitely be unusual. This is kind of combining the material we learned in Chapter 3 with the material from Chapter 6. Alright. Let's see the next question. It's from Chapter 7. Question number 23. So it says the number of chocolate chips in an 18-ounce bag of chocolate chip cookies is approximately normally distributed. As soon as you see the word normally, the words normally distributed, you draw that nice normal curve with a mean of 1252 and a standard deviation of 129. So I'm just going to go ahead and draw out my curve. We know that my mean is 1252. My standard deviation is 129. So before I even read the questions, I'm just going to set up my curve. I think it's really helpful to have this on your scratch paper before you even read the questions so that you can have it all set up and see the full picture before you try to answer any questions. Oops, minus again. So just take that minute, add 3 times, subtract 3 times so that you have your full picture. All right. Part A says, what is the probability that a randomly selected bag contains between 1,000 and 1,500 chocolate chips? So this is part A, between 1,000 to 1,500 chocolate chips. Now kind of visualizing this, 1,000 is going to be somewhere here, and 1,500 is going to be somewhere up here. So that's a very big range that we're going to be using. You can use the chart or you can use normal CDF in the calculator. Your lower bound would be 1,000. Your upper bound would be 1,500. Your mean and your standard deviation. So it's always lower bound, upper bound, mean, and standard deviation. You could get a z-score for 1,000 and a z-score for 1,500 and look them up in the chart, but that would take a really long time. You can just use your calculator. Again, this is under second vars. We'll go to normal CDF. And then 1,000, 1,500, 1,252, and 129. That will give us 0.9473, which again, and we're covering the biggest part of the curve, so that's going to be a number pretty close to 1. So this is round to 4 decimal places, 0.9473. Part B, what is the probability that a randomly selected bag contains fewer? So let's see, part B is fewer than 1125. Fewer than 1125. So 1125 is somewhere right here. Fewer would be anything less than that. So remember down at the bottom we have negative infinity, which in the calculator is negative 10 to the 99. So again, we'll use normal CDF. Negative infinity is our lower bound, up to our target value, 1125, with a mean of 1252 and a standard deviation of 129. We'll run that in. Second vars, normal CDF, negative infinity, 1125, 1252, and 129. That gives us 0.1624. Part C says more than 1175. This time more than, so 1175 is somewhere in here. More than that would be anything to the right, all the way up to the top, which is positive infinity. So this time we do normal CDF. Our lower bound this time is our target value, 1175. Our top value is positive infinity, the same mean, and the same standard deviation. So it seems a little repetitive, but each question is asking a slightly different setup. You just have to remember which side is the lower bound and which side is the upper bound, and you can review that in the Chapter 7 videos. So that's 0.7247. Whoops. And then part D. This is kind of a funky question. I don't think this one's on the final. The percentile rank of a bag that contains 1,000 chocolate chips.